In this lesson, we're going to talk about tangent lines and local linearity. So the very first thing we want to talk about is what is a tangent line? And you guys know from geometry that if you had a circle, that a tangent line by definition was the line that intersected the circle in exactly one point, like this. So we need to broaden that perspective because we're no longer talking about this very small myopic version of a tangent line. In this image, what we have is this blue tangent line, and it does happen to intersect the curve at this point and frankly at this point. But this curve or the line of tangency is only tangent right here, but not right here. So we need to understand why. A tangent line in a broader calculus definition is the line that best models or approximates the behavior of the curve at that point. So what do we mean by that? What do we mean by approximating the behavior of the curve? Well, it means two things. One is that we share an XY coordinate point. So that would be the point of tangency is shared. So it's the Y value of the point at some given X value. And also the slope of the tangent line is identical to the slope of the function at that point of tangency. That is why this point over here is not a tangent line, because whereas we share the same XY coordinate, we do not share the same slope because the slope of the tangent line is negative, whereas it looks like the slope of the function is positive. So in order to best approximate the behavior of the underlying curve, we are required to have a shared point and a shared slope. So that's what's written here in bold. A function f that has a defined slope at some x value has two things in common with its tangent line at that same x value. First, it shares the point of tangency, and second, it shares the slope at the point of tangency, and we denote this as the derivative of f at a, which we say in shorthand as f prime of a. So the derivative is denoted by this prime right here. It is important to note that the tangent to a curve at a particular point is unique in that a function can only have a single tangent line at a given point. That's right here. This is the tangent line. Here's the point. We have a single slope. Okay, so now when we go on to a little sketching activity, what we want to do is for each of the points shown on each of these graphs, so it looks like there are a total of 10 points, I want you to go ahead and pause this video and then sketch with some straight edge, a piece of paper, a ruler, the side of your cell phone. I want you to sketch a tangent line to each graph at each of the marked points. So take a minute and do that, and then press play to check your work. Okay, these start out pretty easy for the first two, and then they get more complicated as you go on to the second two. So let's just take a look first here. You should have a line with a negative slope at the point negative 2, 2. You should have a horizontal tangent line at the origin, and you should have a line with a steep positive slope at this point, which looks to be about 3, 4.5. Second diagram here, you should have a positive sloped tangent line at negative 1, negative 2. You should have a horizontal tangent line at 1, 2, and you should have a tangent line with a negative slope at the point 2, 1. On the third graph, you should have a tangent line with a negative slope that goes through the given point, and it should be that this tangent line intersects the graph. And this is unusual, or it's not unusual in the scheme of calculus, but it's different than the first two images here, where on these graphs, did you notice that the tangent lines never did actually cut through the actual graph? Here, when we have a point of tangency, we have a point of tangency and a slope with a tangent line that is on one side of the graph here, but on the other side of the graph here. And then on number 4, the tangent lines at the point negative 2, 2 and at the point 3, 3 are actually match up exactly with the branch of the absolute value function. And then do you see that I did not draw a tangent line right here at the origin, and we're going to have to talk about that. So let's do some concluding work here. The position of the tangent line relative to the function it models, that should say a t there, depends on the concavity of the function at the point of tangency. So if you look at the pictures above and complete the statements, what we're going to see is the following. when we have a concave up function, so that's this entire first function here, where does the tangent line lie with respect to the graph? Well, do you see how this tangent line lies underneath the graph, as does this one, as does this one? That means that all of the y values on the tangent line are lower than the y values on the graph. So you would say under the graph. Similarly, but conversely, for the second one, we have a concave down function, and the tangent lines are above the graph. Do you see how all the y values of the tangent lines are above the y values on the graph? So when you have a concave down function, your tangent lines lie above the graph. So we used our first two graphs to understand that, but let's look at graph number 3. This is the only graph that we see that's first concave down, then concave up, so we have actually a point of inflection here. That's what this point was, that where we were drawing the tangent line was a point of inflection. So what we see here is for the portion of the graph where the graph is concave down, the tangent line lies above the curve. And for the portion of the graph where the graph is concave up, the tangent line lies below the curve. So these two, under and above, still work in terms of concave up, the tangent line is below the graph. Concave down, the tangent line is above the graph. Now at a turning point, we have several of those here. We have a turning point here, here, and here. And I'm only looking at the labeled points, not all of the turning points. So the tangent line will be either horizontal, as it is in the first two graphs, or undefined. Notice that we did not put a tangent line in here. That's because my slope coming in from the left would have been -1. The slope coming in from the right would have been +1. There is not a unique tangent line here. So I can't say that there's a defined slope and there's a single slope at that point. At the point of at the point of inflection, which is right here, this is the only inflection point we dealt with, this is where the tangent line actually intersected the graph. So the tangent crosses through the graph. And that is so it can be above the graph on a concave down portion of the graph, and it can be above the graph, under the graph on a concave up portion of the graph. Two more points here. At a point on a linear function, the tangent line is what? Well, that's here. We have a tangent that matches the function on this linear portion of the graph. Same here. The tangent line is the graph on a linear portion of the graph. So the tangent is the same as the graph. Last question. At a sharp point, the tangent what? Well, there's only one here. So we want to say that the tangent line is not unique. And we would say that the slope at that point is undefined.